All right, so at the tail end of the part A of 13.6, I had kind of given you a roadmap for where we want to go from here. So I had mentioned that from some point on a surface, say right here, that using the concept of a directional derivative, you can find the slope in any direction you want. Okay? Not a problem. All you need to do is just know your desired direction. Now, let's agree, though, there is, well, from here, there is one direction that you would want to go if you wanted maximum increase, right? So if you wanted, there's lots of directions that you could go from if you were standing here, but there's one direction that would be maximum increase, the maximum slope. And notice that there's also a vector in the plane that points in the direction of your desired goal, right? Well, let's go ahead and say this. So this vector right here, the vector in the plane, this is what we call a gradient. Let's go ahead and use some notation. So the notation that we will use in this class looks like this. Now, if you were an engineering student, it's possible that would be the notation that you would see, but from many of the engineering textbooks I've looked at, instead they use this notation. And I'm trying to think, I'll find out in just a second if it's grad of f. This is what I think it is. So the gradient, so they'll just put grad, grad. So what is this gradient? We're going to talk about it. Well, it's a very special vector. Okay, it is. So first thing to notice, the gradient is a vector. Let's take a look. So we're going to kind of walk through the definition of a gradient, and we'll start with just two variables, functions of two variables. And I'm going to kind of take some notes and make sure that there's a few things that we understand. So, that was right. So this is this notation, grad of f of xy. This would be the type of notation for a gradient that you would probably see in an engineering textbook. Nevertheless, let me go ahead and let's start with the basics. So this symbol, let's start with the symbol here. It is red, if you were reading that. Del, that's that little upside down triangle, del f. Another, I'm just going to kind of go through some bullet points, and then I'll read the definition to you. So another quick bullet point is that the gradient is a vector in a plane. Not in space, in a plane. This is kind of it is somewhat germane, but it is not. You don't have to worry too much about what I'm showing you now. This, just for those that care to know, that del, that upside down triangle, is not a variable. It's an operator. Right, just like dy dx is an operator. It operates on the function and creates a vector. Now, this is, you would read this as del f, but let me, since we're not really interested in just the operator, we're actually interested in the gradient. So, more importantly, you would read this as the gradient of f. I think it's important to point out things like how do we read the notation? Like if you had to read it aloud to yourself or to someone else. That's why I always try to make sure that you understand. But let's go ahead and write the gradient in its entirety. So here it is. You got your partial with respect to x in the I direction, plus your partial with respect to y in the j direction. So again, notice it's a vector. The gradient is a vector. Ready? So you have some multivariable function of x and y, and we have to such that the partials with respect to x and y exist. So the partials must exist, and we have a function, multivariable function of x and y. Then the gradient of f is the following vector. And what it does is, so this is right here, again, this is the gradient. It's going to point in, all vectors point in a direction, agreed? It's going to point in a direction of greatest ascent or descent. In other words, the direction of maximum increase or decrease. And I hope that you can envision quite a lot of applications where you would want to know the direction of maximum increase or decrease. In fact, what you should be thinking is think optimization, right? When we did optimization in Calculus 1, the ways to find maximum, minimum, extrema. We're always, think about it, in everyday language, we're always talking about maximums, minimums, right? What's the maximum speed your car can go, 0 to 60? What is the max you can bench press? What's the minimum cost? We love maximums and minimums, and that's why there's a lot of money to be made in optimization. So maybe fall in love with it. Ready? Let's start with how do we just find the gradient of a function. So here's the function, find the gradient of the following function, and they go a little farther and they tell us what point we are at. All right, well, let me go ahead and write the recipe, right? The notation. So the gradient of f is going to be equal to, well, we need the partial with respect to x, and we're going to need the partial with respect to y. And what you are going to have to be careful with is that you don't put a cosine of theta, sine of theta in here, because that is when you're dealing with directional derivatives, and directional derivatives are not vectors. So in the next page, I'm going to try to just summarize some of these various notations that we've been using, because it's very easy to get them mixed up. But ready? Obviously, we need our partials. So we will begin there. Well, again, you should be fairly good at taking partial derivatives at this point. if you take the partial with respect to x, right, remember the derivative of ln is 1 over x, so derivative of ln x is 1 over x, so the partial with respect to x should be y over x plus y squared. And then if you take your partial with respect to y, this is going to be ln x plus 2xy. As always, if you need to pause the video to make sure you can do these partials, feel free to. Just don't let the video, at least I would advise not to let the video continue running while you're in your own mind trying to figure out the partials, right? Because you're missing things that I am saying post this point. So that's great. We have our partials. Let's now, let's plug them in and form our vector. So the gradient of f is simply y over x plus y squared in the I direction plus ln of x plus 2xy in the j direction. There it is. So again, notice that, so that's, if all I asked was what's the gradient, then this is your gradient. This is a vector function, right? Notice this doesn't give you a direction unless you give it more information. You have to give it an x and a y. In other words, you have to tell it where you are located. So now let's take into consideration that 0.12. We're just simply going to be plugging in x is 1, y is 2, and that is going to give us the actual direction. So, a little bit of arithmetic. You just plug in x is 1, y is 2, gets us to 6i plus 4j. There it is. So that is the gradient of f of f of 1, 2, meaning the gradient of f at the point 1, 2. And I've tried to, they didn't have a graph here, so I just used some three-dimensional plotter, and you can see that. So this is the point in the plane, 1, 2. Now, if you were to plug this point into your function, this is where you would be on your surface. And now, if you were to plot out the vector, 6i plus 4j, I can't quite draw, but that would be the direction that you would want to go to get maximum increase, right? The maximum ascent. Okay, now, what we need to do is, you notice this, all these various notations that we've been using are starting to pile up, and we do need to make sure we understand these, what each of these does and what each of these are. So vector u is, what is that? That's just a unit vector in the desired direction. Okay, now the du, this was what? This was the directional derivative right? It's the derivative of f in direction u. It's not a vector. It's just a derivative. It's a derivative of your function in the direction of u. Right? This del f, this is your gradient. And this is a vector that points in the direction of greatest ascent or descent. I have no idea if that's how you spell ascent. Actually, I don't. I'm not even going to try to spell it. I'm just going to write these letters very close, so you can't even tell if I'm spelling it correctly or not. Haha, that's my tricks. Well, we know these are just partials, right? These are just partial derivatives. But we saw that partials derivatives are still directional derivatives, just in the direction x or y. Okay, so hopefully that kind of summarizes all of the various notations that we've been using. A little bit more information about the gradient, right? So one of the interesting properties of the gradient, and I'm going to say this slow because I want you to be awake enough to hear me. You can, if you have the gradient, right? In other words, you know the direction that's of maximum ascent. You can actually use the gradient to find the directional derivative. Right? That's what's being shown here. That notice that if you take the gradient and you dot product that with u, what comes back out of that is the directional derivative. Right? So you can use the gradient to find the directional derivative. This is a very important formula to have readily available. Just a couple more properties of the gradient. Now, again, we assume that your function is differentiable at some point. So let's think about what would mean if you get a gradient equal to 0, right? If your gradient is equal to 0, what does that tell us about your directional derivative? Well, if your gradient is equal to 0, then your directional derivative is equal to 0. And that's true no matter what direction you choose for u. Doesn't that make sense? That if this right here is 0, if you dot product u with a 0 vector, don't you get 0? So, of course, if the gradient is 0, the directional derivative is 0. Now, it just so happens that if you're just thinking about slopes, right? The slopes, the direction of max increase of that function is obviously is given by your gradient. The direction of minimum increase of that function is just negative gradient. But what you want to take away is that means the maximum slope, right? Because that's right. The maximum slope is just going to be the magnitude of that gradient, or the minimum slope is going to be the magnitude of this, the negative magnitude of this gradient. Okay. I do want to notice that I'm really not practicing a lot of examples on how to do a directional derivative and a gradient, because you'll get the practice from your exercises from your textbook. As long as you know how to do a partial derivative, they're not that hard. I'm going to do one more application. It's going to be in the next video because it's going to take us a while. But I need to give you some words of caution here. So let me read and let's see if you can understand what I'm trying to convey here. So yes, the gradient always points in the direction of the max, the greatest increase or decrease. But that doesn't mean the gradient necessarily points, there's supposed to be a point here, towards the max or the minimum value. Okay. So if you have a surface, and so this is the maximum value, right? This is the max, the extrema. Now, just because the gradient points towards the greatest increase, that doesn't mean the gradient is always pointing towards the extrema, right? It might look something like this. It might look like this, and then like this, and then eventually until it'll get you to your extrema. But the idea is, look, once you leave that point where you're at, the direction of greatest increase or decrease may change. In fact, in the next application, on the next video, I'll show you how that's the case, likely the case. Now I'm going to make a statement here, and I haven't decided if I always have to decide, do I want to prove my statements, every statement, or do I lose my audience? So there is going to be more to say on this statement, but let me just start with a statement that the gradient is normal, right, perpendicular to level curves. I will have more to say on this later. So let me just keep that in the back of your mind. The gradient is normal to level curves. So what do we do when we get back from in the last video? Well, this is a really interesting application. So we want to find the path of some type of heat-seeking particle. Now I might just call it a missile, right? You have a heat-seeking missile. What is the path of the heat-seeking missile? This is going to be a prelude into differential equations. We're going to use some differential equations here. So if you happen to take diff EQ with me the following next semester, awesome. If you don't like me, that's no problem. I might not like you either, but nevertheless, we're here. We have to put up with each other. So this is going to just give you a taste of what we're going to be doing in diff EQ. But the idea is, how do you find the path of a heat-seeking missile? All right, so I will begin this problem in the next video.